Hi everybody, and welcome to a new video in the video series on systems biology, digital twins and AI. So we are still in block 2, and in the previous video we looked at local optimization approaches to solve this problem of finding the parameters that minimizes the cost function. And now consequently in this video we'll look at global optimization algorithms. And at the end of the video on local optimization, we look at the Nelder-Mead, which has this simplex that moves here by doing reflections and extensions and shrinkings and so on. And we see here the problem that we need to overcome. That if you sort of start this simplex here, you will end up here. But if you start the simplex over here, you will end up in this local optimum. And if you start it here, you will end up in this local optimum, and so on. So you need somehow to be able to escape from local optima. So global methods are often called also meta-heuristics. So they are sort of stochastic global methods. It's one important class of global methods that combine a local solver, so the ones that we saw on the previous slide, or in the previous video, with some heuristic global component that in one way or another allows you to escape from local optima. So in this video, we will look at some of the most well-known alternatives. The first one is called simulated annealing, and this one will be combined with precisely this Nelder-Mead approach, this simplex that's moving around. We look at scatter search, genetic algorithms, something called particle swarm, and then in the end we'll sort of wrap things up. Okay, so let's start by looking at simulated annealing. So here we want to see the optimum, and note here that as the temperature is shrinking, you're going from moving all over the place to looking more and more in the best place. So in the beginning, when the temperature is high, you're searching all over the place, but then as the temperature is shrinking, you are looking more and more only locally. So this was an approach that is inspired by the cooling process of a protein or something else that sort of needs to find its optimal configuration. And in the beginning, the temperature is high, so it's all random movements. But then as the temperature is shrinking, it's more and more crystallizes. So if we look at the basic algorithm and then in the version that we are using in the MATLAB toolbox, you have some initial temperature that's typically high, and you have some start guess, which is the first point where you start the optimization, and you have a cost function. And you keep going while some kind of looping variable is not at its maximum value. So the first step is to change the temperature, which generally implies lowering it according to some schedule. Then you take some kind of step. So here in a simulated annealing approach, you need to combine it with some kind of stepper. And then you make a decision based on drawing a random number between 0 and 1 and some kind of calculation depending on the cost that you got for this new tentative step that you got with this stepper. So depending on if the probability that you calculate from the cost function at this new tentative step compared to the cost function at the previous step. So this allows you, according to some formula, to calculate a probability. And if this probability is bigger than the random number that you draw, then you pick the new number, and then you repeat. So that's sort of the heart of the simulated annealing. So now let's look at how how we use this to return the sort of optimal parameter in the end and the optimal cost. So in the computer lab and the computer the MATLAB toolbox, we are using a version where the step 1, the changing of the temperature, is done in steps. So you keep the temperature constant for some time, and then you figure out what was the best parameter that we encountered during this higher temperature, and then you start there when you when you lower the temperature to do a more local search. So you sort of do an increasingly more and more local search, but you do it in steps and you bring on the best one. So that's the way that we deal with the temperature. The stepper, so the step 2, the one to provide some kind of tentative step, is this Nelder-Mead, this simplex that might take a corner of the triangle and reflect it, or that might take the best point and after a reflection, if it's a good improvement, then it steps more in this direction. So this simplex approach, that's the one that's used to take the tentative steps. And then this probability calculation, it's so that you have probability 1 if it's an improvement. So if the new tentative step is lower than the previous one, then you take it. And otherwise, it depends on how much worse it is. So if the cost for the tentative new step is bigger than the previous one, you might still take it. And this depends on the relationship between the cost increase, so delta V here, V of P for the tentative step minus the cost for the old one divided by the temperature. So if the temperature is very high, then this is a small number and you're taking the minus exponent. So you're dividing the small number. So this is a big number. And then it's a high probability that you will actually take the step. And vice versa, if this improvement or if this step upwards in the cost function landscape towards worse solutions, if this is much bigger than the temperature, then this is a big number and you divide with the big number, so the probability is small, so it's very unlikely. So in the beginning, you will take lots of steps in all sorts of directions, searching all over the place. But then as the temperature is lowering, the probability of you going uphill, so to say, towards in the cost function landscape, and downhill if you are finding the maximum, so that you're going sort of in the wrong direction, the likelihood that you do that is getting lower and lower the lower the temperature is. Okay, so that's the simulated annealing. You have this temperature, which sort of allows you to search globally and not care about getting stuck. And then in the end, when you have found the most promising places, then that is sort of where you're searching. So let's look at the next approach called scatter search. And this was introduced in 1977, and it's sort of been gaining momentum, and now is one of the more popular optimization algorithms. And the core sort of unit, the core thing that this revolves around is a ref set. And this reference set, is something that has two parts. It has the best parameters that we found so far, and it has parameters that are used to sort of get you to move away, to invent new directions to go in that you haven't searched for yet. So these are the best parameters we found so far, and these are parameters that simply are there to make you able to unstuck yourself from a local optimum. And then you are sort of updating this ref set using 5 functions. So let's have a look at these five functions. So in the beginning, you need to just create the ref set. And you do that in the same way as you do when you do just local optimization when you have multiple starting points. So this is typically how you, if you only use a local solver, this is typically how you do it. And that's using something called Latin hypercube sampling. So here we see it in action. So you divide each parameter dimension in sort of some discrete levels. This is often in a logarithmic space, so that if you have different orders of magnitude, you're not sort of only looking at the biggest order of magnitude, but you're actually looking across all the orders of magnitude. And then you do the same, so you get this sort of grid in some hyperdimensions. So it's not only 2 dimensions typically, but if you have 10 parameters that you optimize over, it's the same idea. It's just you can't draw it. And if it's 10 dimensions, you can't fill all of these boxes, all of these sort of grids here. You can't fill them because 10 dimensions is simply exploding. So what you're doing instead is that you're ensuring that for each parameter and each level, you appear at least once. So here we appear once, here we appear once, and so on. And in the same way for the other parameter, here we appear once, here we appear once, here we appear once, and so on. So this allows you to sort of get a decent coverage across the entire parameter landscape without having to fill all combinations. So you're sort of spreading around in a reasonable way, in a maximal way, in some sense, in a way that doesn't explode when the dimension that you're searching in explodes. So this is called Latin hypercube sampling. This is just to get started, to have a first sort of iteration of this ref set. And then you use step 2, which you come back to all of the time, which is to do some kind of improvement, which is basically to take these starting guesses that you had here and then optimize so that you sort of end up in optimal places. So here you end up in these 2 clusters. So this is probably some kind of local optimum, and this is probably some kind of local optimum. And this is typically done using some kind of local optimization. So the methods from the previous video. And then you want to, given that you did this local optimization, you have new parameters, which are the optimal versions of the original ones that you had before. And then you use these to sort of update the ref set. And typically here you want to take those that are the furthest away from each other. So here, this one is furthest away from these ones over here. So here you would, for instance, pick these ones down here and this one here. Okay, so that's sort of to get started. And now we'll see how we loop back to this and loop back to this and loop back to this. So in the ref set, we have these optimal parameters, the best ones we found so far, and we have the diverse parameters, the ones that are supposed to make us go in different directions. So in step 4, what you're doing is that you are taking these optimal parameters and the diverse parameters, and you do combinations of them. So you get smaller subsets of parameters, and you get many such subsets. So you get many subsets that take some optimal parameters and some diverse parameters. And then you combine them. So, and this combination is that you take an existing parameter and you take another existing parameter from your subset here, and then you somehow combine them. You take a parameter point that is between them. So if this is the diversification parameter and this is an optimum one, this one allows you to step in a completely new direction, so to say. So this is sort of the idea, that you use these diverse parameters to combine them with the optimal parameters. So then you have some completely new directions that is sort of based on your good solution so far, but you step in sort of new directions. And then you do the local optimization. You go back to step 2. And after you did this improvement, So you have the best parameters that the local solver allowed you to find based on all of these parameters that you have. Then you have some more optimal parameters. So you have a sort of bigger set here. And then you do the update approach, which is the one I described on the previous slide, where you take the ones that are the furthest away, this max-min approach. Okay, so in this way, you sort of get back to the ref set again. And then you go back to step 4, which is to generate its subsets, combination, improvement. And then you do step 3, which is to update the ref set, and so on. So you go round and round and round and round. And this is how you sort of all the time do this local optimization, but you also allow yourself to escape from these local minima. Okay, so that was the scatter search. Now let's go to the genetic algorithm. So this was proposed already in 1950, and it was quite popular, especially in the 60s and the 70s, both in biology, but also in optimization, which is what we're talking about today. So the two central components that sort of is at the heart of the genetic algorithm is to do basically the idea of natural selection, which is that you have some random mutations and cross-fertilization. So you sort of you have the ability to have things happen to your parameters, basically at random, and also for parameters to cross-fertilize each other, basically to create a baby, and which has some properties of these parameters and some properties of this parameter. And then apart from that, you have some natural selection. So the ones that are the most competitive, the ones that are the best, those are the ones that are most likely to survive in the next iteration. So this is sort of completely inspired by the idea of Darwin and the natural selection. And today you sort of generalize this idea to something called evolutionary algorithms, which is sort of building on the same ideas. It's just slightly more modern and generalized update of this. So here you can sort of notice that you sort of have the same ideas coming back all the time, that you want to combine parameters. You have this also in the scatter search, and then you have some kind of way of picking the best ones. So here there is typically not a local optimization algorithm involved. So finally, let's look at something called particle swarm optimization. And this is basically based on the idea of sort of collective intelligence. So the idea is that you have a set of particles. Here you have a flock of birds, or a murder of crows, or whatever birds it is. And each bird here has some. So sort of the idea is that somehow these can collectively make these beautiful patterns, and the question is, can we sort of be inspired by that to create a new optimization algorithm? And the idea is that each bird here has or each particle has a current position and a current velocity that it's doing now. Sort of has an inertia to keep going in the same direction it was going in. It has a place with the lowest cost that this particular particle has ever found. And this is sort of, it has a tendency to go back to where it has been that was its own personal best. And then it also has an information about what is the global best that any bird or any particle ever found. So you have this sort of current velocity or the inertia. You have the cognition velocity, which is that you remember where you were ever at your best. And then you have the sort of socialization velocity that they all have a tendency to go to where the best particle found its best ever for the entire flock, so to say. And then you combine these. So if you want to sort of, for each particle here, you want to have the next step, pi plus 1, then it's where you were before, plus some step in this velocity space where you combine these three velocities, the inertia, the socialization, and the cognition. So you have some kind of weights to balance them together, and then you have some random numbers, meaning that you combine them also in a slightly random way. And this allows you to sort of both have go in good directions, but also have the ability to sort of go in new directions. Okay, so we have all of these different options. Which global optimization or meta heuristic is actually the best? Well, there is no consensus about this. And here I just picked one of the papers that looks at this. So this is done by a group that is specialized in local optimization solvers. And naturally, those type of groups tend to find that the global optimization algorithms that we see here in gray, for instance, that don't have any local optimization involved in it, they are not so good at finding the best optimum. So here we have the cost function on the y-axis, and they are sorted so that for each line here that goes down, which is one optimization solver, the best ones are to the left. So here, even the best ones that were ever found out of 100 attempts for these global optimization algorithms that does not have any local solver, they never really find the really best parameters that are down here. So they find that you need a global optimization, or you need a local optimization to be competitive. But then they find that as long as when you are using the local optimization algorithm, you are using state-of-the-art approaches like these sensitivity equations that we talked about in the previous video, which is a way to calculate the derivative in a clever way. As long as you are using that and some other sort of state-of-the-art tricks, then it doesn't really matter which sort of global optimization algorithm you are using. You can just use this multi-start approach. That's what they find, but again, there is no consensus on this. So I don't want to say that this is the sort of consensus. Some other groups that are typically better at global optimization algorithms will maybe find that global optimization algorithms that there are differences and that they are better than just a multi-start approach. So the final thing I just want to say that in a paper like this, when you're comparing many sort of state-of-the-art optimization algorithms, you typically have a list of different optimization algorithms. And here we just see from the same paper as we looked at before, some of those. So we have the evolutionary strategy, which is this natural selection thing. Covariance matrix, we'll look at that when we look at parameter uncertainty. We have the genetic algorithm. That's again the natural selection. We have the particle swarm, where we have these three velocities that we combine. We have different variations of those. Monte Carlo we'll look at in one of the next coming videos when we look at parameter uncertainty. Trust region, that's the one for the local optimization, where you ensure that you don't take too long steps. Latin hypercube, that was the thing where we did a spread of the initial conditions. Finite differences, that's the other way of calculating the derivatives, where you do two simulations and you take the difference. Sensitivity equations, that's where you do a big, instead of doing two simulations, you do a simulation with an expanded set of equations, and so on. So you see here that in this sort of fairly recent paper, where you look at all of the state-of-the-art approaches, already now with these two videos, you have seen all of the central concepts that sort of appear. So now you should have with with these two videos, you should have a decent understanding of the state of the art on the scientific forefront, so to say, in both local and global optimization and their combinations. So that's the end of this video. Thank you for listening.